we're just going to look at a couple of more examples about how I can create Maclaurin series that are new from Maclaurin series that are already known. So you've seen this front page a couple of times. Here are the known series about this group, the geometric series. So let's do two more examples. Okay, suppose I want the expansion of x squared over 2 minus x. The Maclaurin expansion for x squared over 2 minus x, and I don't want to go back to the original definition. Well, I recognize that this looks an awful lot like 1 minus x, and I already know what the expansion of 1 over 1 minus x is. That's my well-known geometric series, summation n running from 0 to infinity, x to the n, and I also know it converges when the absolute value of x is less than 1. All right, so how do I use this to get this? And the answer is, well, upstairs I could factor out an x squared. That just leaves 1. And then downstairs, do you notice this form has a 1 there? So I want a 1 there. But right now, there's a 2. So what do? I factor out a 2 downstairs. Now when I factor it out, it's got to come out of this. That gets me the 1 that I need. But it also has to come out of this, and that gives me x divided by 2. So x squared over 2 minus x can really be written as x squared over 2 times 1 over 1 minus x over 2. And now compare this piece with this piece. Everywhere I see an x here, I want to replace it with what? X over 2. So when I do that, I get the x squared over 2. Then now I'm going to write this series, summation n running from 0 to infinity of what? Well, everywhere I see an x here, I replace it with x over 2, so I get x over 2 to the n. All right, so, and now I can rewrite this as what? X to the n over 2 to the n. I still have an x squared over 2. And if I want to carry this along with me, this converges when the absolute value of x is less than 1. But here, x over 2 is playing that role. So it's going to converge when the absolute value of x over 2 is less than 1. All right, now what do? Well, now I just pass this inside. There it is. And I use my rules of exponents again. X to the n times x squared is x to the n plus 2, and 2 to the n times 2 is 2 to the n plus 1. So there is the function I was interested in, and there is its Maclaurin expansion. And that's the same Maclaurin expansion I would get if I actually used the definition. And now, if I'm curious about where it converges, absolutely, well, it converges absolutely when this is true, which is when the absolute value of x over 2 is less than 1, or multiplying both sides by 2, when the absolute value of x is less than 2. So there you have it. The expansion for this is that, and the interval of absolute convergence is here. All right, now let's look at our last example, which is an interesting one. Suppose I want an expansion for the natural log of 1 plus x. Well, I think natural log, the integral of 1 over x dx is natural log the absolute value of x plus c. Now, I'm not going to mess with the absolute value. I'm just going to assume this thing is positive anyway, so 1 plus x is greater than 0. That's what I'm going to look at. And I also know that 1 over 1 plus x remember that was my little special geometric change, is n running from 0 to infinity of minus 1 to the n x to the n. Well, so how does all that help here and here? And the answer is, the natural log of 1 plus x then is the integral of 1 over 1 plus x dx. But 1 over 1 plus x is this, so it's the integral of that. And so all I have to do is integrate this term-wise. Well, minus 1 to the n goes along for the ride. I get x to the n. The integral of that is what? My rule says what? X to the n plus 1 over n plus 1. So there is it integrated. Now, it's an indefinite integral, so I'm going to have to add an arbitrary constant c, and I'm going to have to figure out what that arbitrary constant is. How do I do that? Well, I plug in x equals 0. So when I plug in x equals 0, I get natural log of 1 plus 0, which is natural log of 1, which is 0. And when I plug in 0 over here, all these have positive powers of x. So when I plug in 0, this whole thing goes away. That is, its value is 0. And what I get is 0 is 0 add c, which tells me c equals 0. Now there's a lot of zeros there. All right, so the point is my answer becomes this with c equals 0. And I just write it right here. So I get natural log 1 plus x is summation n running from 0 to infinity of minus 1 to the n, x to the n plus 1 over n plus 1. Now guess what? Look at that. And now let's go up here to, there is the expansion of the natural log of 1 plus x. What I get? Minus 1 to the n, x to the n plus 1 over n plus 1, n running from 0 to infinity. That, my friend, gives me a warm, fuzzy feeling. That's exactly the answer I got. Math is true. Well, I just thought I'd add a few more examples, and there you have it. Bye.